Hi everybody, let's continue our discussion of gases by looking at something called the kinetic molecular theory, or KMT, of gases. And so kinetic molecular theory in a nutshell says this. It says that as you increase the speed of gas molecules, or the speed of any molecule, right, you gradually move state of matter-wise from a solid to a liquid to a gas. Right? And we know that because as we increase the temperature, we increase the kinetic energy. Why do we do that? Because we're increasing the velocity of these gases or of these molecules. And gradually, they begin to slide past one another to form liquids, and then they basically break the surface and become gases. And so we're going to look in particular at the gas component of this today. And at the end of the discussion today, we're going to come back and talk about the difference between something called an ideal gas, which is basically what we use all of our math for in this unit. We talk about math for ideal gases, but we'll talk about how those differentiate from something called a real gas. So let's first define 5 assumptions of the kinetic molecular theory. So these are some things that we assume to be true for ideal gases. Number 1, gases, if you had a sample of gas, take up a really large volume. But relative to the volume that they occupy, the volume of an individual molecule, so if I were just looking at the size of this molecule, relative to the volume of the box that it's enclosed in here, right? So there's the big volume of the box that you see outlined there. And relative to that volume, the volume of this particle itself is really, really small. So what we can do is consider the volume of the gas particle itself to be negligible or to be not present. Relative to the volume that it occupies, the molecule really doesn't take up any of the volume. So that's the first assumption of KMT. Second assumption is that collisions between the molecules, when they happen, are going to be perfectly elastic. And when we say elastic, another way of saying that is that kinetic energy is conserved. But what the heck does that mean? Kinetic energy being conserved means that no energy is lost to the collision. So imagine you're driving on the road and you have a collision, right? And it's a collision where both cars are totaled. Luckily, everyone is safe, but the cars are a mess. And so what happened there was a lot of energy from that collision went into crumpling the cars, and it made a really loud noise, and perhaps there was some heat given off from friction, right? So a lot of energy got dissipated quickly, and that's why the cars look like they're a mess right now. In a collision between gas molecules, we are saying that they bounce off one another and just keep going at the same velocity in a new direction. So imagine that in a car collision. You have a car moving around this way, you have a car moving along this way, they have a collision and they bounce off and just continue going in a different direction, but at the same speed, right? No damage. That's what we're saying for these gas molecules. Kind of crazy that that would happen in a car collision. It wouldn't. But in gas molecules, this is one of our assumptions of the kinetic molecular theory. And by the way, we said that pressure is the cause or is the product of a collision between a gas molecule and the wall of a container. And the collisions that you see here between different molecules, that doesn't cause pressure. We're just bouncing off other molecules until we bounce off the container. So pressure from gas molecules only is a result of bouncing off the walls of a container. Third assumption of KMT is that gases are in rapid, continuous, and random motion. And because they're in this rapid motion, they possess energy, kinetic energy, in fact. We'll get more into kinetic energy here in a second. But there's no guide to the direction that these molecules are moving, right? They're in complete random motion, but it's really, really fast motion. Our next assumption is that there are no forces of attraction or repulsion between gas particles. So basically, if we had a gas particle over here and we had a gas particle over here and they were moving past one another, they would move past one another freely without having any interaction at all. And you can think about in real life, maybe this isn't quite the case, because if you think about a water molecule, water is this polar molecule. It has partially positive and partially negative sections, and so if it's moving past another water molecule that looks like this, let's say they're both steam, then we're going to have an attraction between the partial positive and the partial negative components of these gas molecules, these water molecules. So there's one instance where we don't really see ideal gas behavior with real gases, but we'll get there further in a second. Our final assumption of KMT is that the energy of the gas particle is dependent on its temperature. So why is that? Well, as you increase the temperature of a gas particle, you increase its speed, you increase its velocity. And kinetic energy is defined, we'll talk about this a great deal in physics, kinetic energy is defined as 1/2 the mass of a particle times velocity squared. Mass is unchanging for gas particles because the molar mass, if you look at the periodic table, doesn't change, right? So oxygen is always 32.00 grams per mole. Water is always 18.02 grams per mole. So the mass doesn't change. The only thing that's changing is the velocity at different temperatures. So velocity therefore increases or decreases the kinetic energy. And so kinetic energy really is a measure of the temperature of gases at various, let me say that the other way. Temperature really is a measure of the kinetic energy of gases in certain conditions. So if we want to figure out, hey, what energy is present in this gas, we measure its temperature. Okay, so those assumptions of KMT give rise to some properties that are pretty predictable, and we know this, right? So if you think about a gas, it expands to fill its container. If you had a nice water bottle like so, if you had a solid in that water bottle, it would just sit on the bottom, right? If you threw a rock in this water bottle, it would just sit down here and do nothing, right? If you filled this water bottle with water, well, it would expand on the bottom, but it wouldn't go anywhere unless you move the water bottle. But gases, on the other hand, they take up all of this volume up here until they're released. And if you take the lid off, they're going to keep expanding to fill their container, right? They're just going to go everywhere. So that's one property of gases because of that continuous, rapid, and random motion, and because there's nothing holding them together, right? There are no forces of attraction between those molecules. Another property that gives rise here is fluidity. So gas particles, much like liquid particles, but more so in gases, are able to easily slide past one another. And this is a result of assumption number 4, which is that there are no forces of attraction or repulsion between these gas particles, right? There's nothing slowing them down or stopping them. Another property that we see with gases is they have very low density. So because they expand, and we're going to consider their volume to be negligible, then density we said is mass over volume. They have a really, really, really large volume that they're occupying, right? So they're expanding to fill this entire container that we've drawn up here. But in that container, the gas particles themselves are really, really tiny. They have a really, really small gas. So therefore, they have a really, really low density. And you can think about it's really not a problem at all to go skydiving through air, right? Because you're not impacting any particles that are very close together or dense. But if you forget to open the parachute and you encounter, let's say, the ground is pretty darn dense relative to the air, and so you're going to have a pretty bad day if you encounter the ground at high speed while skydiving, right? So impacting more and more gases, no big deal, they're not dense. Impacting dense ground, big deal, problem. Another property of gas is that we can easily compress them. If you've ever used, let's say, a propane tank to grill food, or you've ever gone scuba diving with a compressed oxygen tank, then you know that you can compress gases. Even if you've ever seen a car tire, which we probably already all have, we know that we can compress a whole bunch of gases into a smaller and smaller area, like so, and then we can increase their pressure by doing that. And the reason we can do that is because they're really far apart. They take up a really large volume, and so we can crunch them closer together because there's a lot of room there for us to compress. And the final two properties we'll discuss are something called diffusion. So that means if you have two gases, over here on the left we have hydrogen, over here on the right we have nitrogen and oxygen. If we open up a valve in the middle, those two gases are going to mix, and we call that diffusion, similar to water, except we're not rushing towards an area of high concentration because we're kind of going both ways here, right? So the oxygen's moving from the right side to the left side along with the nitrogen, and at the same time the hydrogen is moving the other way, and they're going to mix until they have a completely uniform mixture. And similarly, effusion means if you have a hole in one of these containers, so you see this little hole down here, the gas molecules are going to escape out of that hole very quickly. And why is that? Because they're in really, really constant and really, really rapid motion, so they're able to leave that container very easily. Okay, so a lot of those properties are things that probably are rather familiar from our everyday lives, but we want to talk about here the difference between real and ideal gases. So let's think about real versus ideal gases here for a second, and what might be similar and what might be different about those two things. So first off, we've drawn an equation up here at the top of the page. This is called the van der Waals equation. The van der Waals equation looks a little bit more complicated than an equation that we'll talk about here in our next video called the ideal gas law, which states that the pressure times the volume of a gas is equal to the number of moles of that gas times a constant times a temperature. And so if this is the ideal gas equation, you can notice that the van der Waals equation is a little bit more complicated. We are not going to use the van der Waals equation in class. It's not something we'll touch. But I want to show it to you here to note why we have this big distinction that we're making between real versus ideal gases. So all of the different assumptions I just talked about, all of the different properties I just talked about, those are for ideal gases. Now, real gases are really, really similar to ideal gases. And in almost every application that we see in everyday life, we can assume that real gases are behaving ideally. So we can assume that they have really low density. We can assume that they're compressible. We can assume that they have this average kinetic energy that we can measure. It turns out under certain conditions, those properties change. And that's why we need this van der Waals equation. If you go onto a college level course or an AP level course, you'll learn this equation. And it has a correction factor on the pressure that corrects for intermolecular forces. Because as I showed you with water, it turns out that real gases might have interactions between gas molecules, right? So there could be an attraction between positive and negative areas. It also has a correction for the size of gas molecules. So the volume is not entirely negligible of a gas molecule relative to the size of the entire container that it occupies. And so this equation allows us to basically do the same math that we'll do here in a second for ideal gases, but with real gases. And so for today, one thing that's important for us to kind of understand is that there are certain conditions when real gases don't look ideal. What are those conditions? Well, if we have a high pressure situation, then relative to the volume of the container, right, one of the ways we can get a high pressure is to decrease the volume. So let's imagine we've done that. If we have a decreased volume, a really small volume here, the gas molecules in that small volume, there are a lot in here, right, they're now really close together, and relative to the size of that whole container, they actually do take up some of the volume. So we can no longer consider the volume of a molecule itself to be absolutely zero. This also happens at low temperature. So at low temperature, we don't have a ton of kinetic energy. Remember, kinetic energy is equal to 1/2 mv squared, where v is velocity, which is dependent on temperature. And if we slow down our gas molecules quite a bit, we don't have a huge kinetic energy. It's really hard for these molecules to glide past one another. So that doesn't really follow the predictions that we made about ideal gases. And finally, if we have polar gases, like the water that I drew, polar gases have attractive forces, right? There are areas of partially positive and partially negative charges. And so those areas have an attraction with one another, and it's really hard for those gases to slide or glide past one another. So again, this is kind of a weird idea how real gases and ideal gases deviate, but what we're saying is that all around us, there are these real gases, and we can make predictions about the real gases using this van der Waals equation that I showed you. But for this class, we're not going to employ this equation. We are going to assume that all gases behave ideally, even though we know they don't really. And we're going to employ this equation because it's close enough. It's really darn close. And we want to know that that equation works really well for most gases, except when we get into these situations, when we get into like a low volume situation or a low temperature or a situation with polar gases, then the ideal gas law doesn't work so well. So we'll introduce the math behind the ideal gas law in our next video.